it. This is better if someone else records it, then I can see what you hear. Okay, then you started the record.
I think I did, yes.
Okay, perfect. Then now you're responsible for recording. I will present the lecture, and afterwards you can stop it, and then there will be this video in the chat for everyone. Okay. Can you see our screen now? Can you see the screen and the slides, the PowerPoint slides? Oh.
Now they are in the big picture, yeah.
Yep.
Now they're in the big picture.
Yeah, perfect. Presentation mode.
Perfect presentation mode. And Mr. Schröder, you see it on the video. Huh?
I do, yes.
Okay, perfect. Then you record it, you see it, and we share it together. Okay, we start our first lecture about fluid energy machines. And of course, if you have any questions, please feel free to ask, no problem. In our first lecture, I want to present you a kind of fluid energy machines. They are more easy, and we want to talk about propellers, fans, and blowers. And I want to present you some first step with our simulation tool, SimCenter Amazon. SimCenter Amazon is a free tool. You can download it. I will show you how to do it. Everyone can use it and can try it around with it. Okay. So what are the objectives for students in these classes? The students should be familiar with the working principle of fluid energy machines. The fluids should get a slight physical and thermodynamic background. We are not here in physics or thermodynamics. We don't want to go too deep into detail, but fluid energy machines are often a good example for thermodynamic problems. And I want to teach you a bit about simulation and about Amazon. And of course, the students should learn the English language. So please always talk English. Please don't talk German or other languages. Try to use the English language and try to speak English. And of course, the exam will also be in English. Yeah, you have to answer in English. Okay, here are some literature. Yeah, most of this are in German. Yeah, I have to fix it a bit. I have to find some English literature. Maybe I will add it. But up to now, this literature is unfortunately only in German. I think I will change the slides a bit. I will add some English parts to it. Okay. Yeah, here are some English already, but I will add additional English books here. And most of the books can be downloaded online. Of course, we have also a lot of books in our library, and now the guys or the students that are able to go to the library, yeah, it's a bit problem now because of the pandemic, Corona pandemic. The students that can go here can have a look, and they will find a lot of books about turbo machinery or pumps in the library. Okay, what are fluid energy machines? In more or less, fluid energy machines are thermal energy systems, and we want to divide the fluid energy machines on one side into flow machines and in displacement machines. Flow machines have rotating parts. For example, flow machines are gas turbines, steam turbines, radial compression machines, or rotary pumps. And in a flow machine, we don't have a big pressure difference. In most cases, we have high velocities, and the fluid will rotate some parts, yeah? And then we will produce energy or electricity with these rotating parts. On the other side, we have displacement machines. Maybe you all know displacement machines, for example, from your pump of your bicycle. That is a displacement machine. You have a piston or a rod, and you all know diesel and auto engines, and these are also displacement machines. We can also have piston expanders. Maybe you all know old steam locomotives, old steam trains. They had piston expanders. But in this lecture, I will show you also modern piston expanders. It's a quite interesting topic up today. I also developed a piston expander for waste heat recovery at the company of Bosch. I will show you a bit about it. Then we can have also piston compressors that are piston compressors are not used so often anymore. In most of the cases, we use radial compressors with a really high velocity, for example, for turbochargers or for other compressors for if you have some airbrush or so, for this kind of facilities. But in former times, we had also big piston compressors. Nowadays, they are not used so often anymore. If you had the chance to visit Völklingen, of course, for our Finnish students, it's a pity that they are not here in Germany, but maybe you come a bit later. Yeah, maybe you come at the end of semester. We will see this, but you should always go to our big steel factory in Völklingen. It's a museum now, and there you can see really big piston compressors for compression of air. And of course, we can also have piston pumps. Piston pumps for water are also used in many facilities. Okay, what is a big difference? We can have energy, and we can have energy flow, and we can have also power and power flow. So here, FEM, we have our fluid energy machines, and normally in a fluid energy machine, there goes work here with W inside our fluid energy machines, and we get some heat from it. And in most of the cases, this is also the heat is not wanted really because it's a loose. And we also have a mass flow and a workflow. On the other side, we can make a balance about the power, and we can also balance the power that goes into the fluid energy machines, and the heat flux goes outside, and the power that goes outside the fluid energy machine. This is two ways of balancing. And there's also another way to make an order for power and work machines. If we have our fluid energy machines, so we can speak about power engines, and we can speak about work engines. We can divide it in these two main parts. What are power machines? Power machines are, for example, water turbines. A fluid, here in this case water, will flow through the turbine and will produce electricity or work. Yeah. Or we can have a steam and gas turbine. In the steam and gas turbine, the steam will flow through the turbine, or the gas will flow through the turbine. It will expand in the turbine, and then we get power. Or you all know wind turbines or windmills. This is also an interesting topic here in this lecture. I will teach you a lot about wind turbines because we have really good connection to wind turbine companies. We have a big wind turbine company here in Saarbrücken, in the Saarland, in Neunkirchen. It's called the company Vensis, and I can tell you the Vensis that were former students of the HTW University, and they founded this company in the early 90s of the last century, and then they get really successful with this company. And I can teach you a bit about it. I think that's interesting. And then we have on the other side the work machines. And the work machines, in the work machines, we have to spend energy, we have to spend electricity or mechanical work, and we will produce pressure, for example, by a compressor, or we will produce fluid flow by a ventilator, or we will produce a water fluid flow with a pump. So we have work machines and we have power machines. Okay, we will start now with work machines. In work machines, I think I've explained this already. We have in the work machines, we have mechanical energy, and we will convert it into fluid flow energy. We can have rotary work machines or piston. Okay, and we have a lot of examples. Fluid energy machines are not really new. It's a quite modern business, of course. It's really wanted nowadays. We have a lot of projects from industry about fluid energy machines. For example, I had a research project now about filters, and during this Corona pandemic, filters are really needed. We develop new filters now, but these systems are not really new. And here you can see a big building in Liverpool, and this building was built for fans. It was in Liverpool in former times there were mining facilities, big mining facilities, and in mining facilities you have to blow the air down into the mines, and they built this big building. Here you can see inside where fans have been inside, and the air will be sucked into our ventilator and will be blown down into the mines. And if you come to Saarbrücken, or if you, of course, if you have been in Saarbrücken, maybe you can visit our innovation campus in Burbach. And this is an old mining facility. And there you can see similar, really big fan systems where the air have to be blown down into the mines. And this is a really old business. Here's an old painting from the medieval times. And also in former times, the miners had to blow the air down into the mines to get fresh air down in the mines. Okay, though it's not a new business. I think even the Romans had this kind of facilities. Here you can see a big blower and a big fan in our laboratory. And if you come to our laboratory in Alt-Saarbrücken, now it's a bit, I'm a bit sorry, we can't show you all these parts here in reality, but I can show you some pictures about it. This is our big wind tunnel. We have installed it in our laboratory. You can see it, and it had a big blower and some wind channels. And maybe we can show you later a bit about it, or I can lead you around if the Corona crisis is over. Here you can see our fan. Here the wind tunnel is finished. Here you can see the big fan, and it has about 75 kilowatts of electric power. So it's like a small car. You can compare it with a small electric car. Here you can see the tunnel, and we always had we just finished a doctor thesis here in this wind tunnel, and we always had a lot of bachelor or master theses. So if you are interested in this kind of research, it's no problem. We can do also some additional research. Okay, so let's have a look at the fans. I think you all know fans. Yeah, you all know airplane. You know the propeller of an airplane, and you all know this kind of fans. It's a computer fan or a fan for electric facilities, and you know it rotates. It will rise the fluid flow of the air. But if you look slightly at the pictures, you see here a big difference. Here we have an open fan for this airplane. So open fan means there is no duct around the fan. And if you have a slight look at this computer fan, we have a duct around it. Yeah, there is a housing around this fan. We call it ducted fan. And I will come to this point a bit later, because the efficiency is much higher if you have a duct than if you don't have a duct. So if you can use this duct around your fan, you can rise efficiently very much. Okay, here we have a look at our propeller. Yeah, we have omega. This means the velocity of the angle. We have, of course, our wings in the propeller, and the wings had to be shifted a bit because it's always important, if you have a wing, how big is the angle of attack? How is the direction of the air that hits the propeller? This is really important to calculate the force and the velocity of the wind. Okay, here you can see it again. We have our propeller. Propeller rotates, and we have a diameter of the propeller. We have the angle of the blade. This is the angle of attack. And we have the velocity of the wind. I think it's a simple setup. You all know it. But if you go into detail, and have a close look at this blade, it's not so easy anymore. Yeah, this design of this blade is really difficult. You need to make simulation with a computer. You have to design it really closely, and there is a lot of knowledge and science needed to design it in detail. But up to now, it's fine if you know the simple principle. And I can tell you, I just made a bachelor thesis with a student about the design, and we made a simulation of this propeller. And what is really cool nowadays, we can print these propellers really fast now, because we have 3D printers, we have additive manufacturing. So nowadays it's really easy to make a design in the computer, to plan it with a simulation tool, and then you can just print it and try it out. So that's something where we spend a lot of time currently to print these propellers and to test them in the wind tunnel. Okay, but up to now, we keep it simple. First, if you start looking on work machines, the first big important, let's say, quantity is the power. Of course, you can calculate the power of a work machine, and you can calculate it by the mass flow, the specific energy, and the efficiency. If you divide it by the efficiency, you get the power of the work machine. Here, a small question. Specific energy. Do you know what the word specific means. Specific has a special meaning. Specific. Maybe, no, I cannot really see the chat. So I start the chat. Hello, are you still here, guys?
Yes.
Can anyone tell me what the word, maybe you know it from physics or thermodynamics, what does the word specific mean? Do you have an idea? We will use it more often in future, specific. You know it from normal life. Okay, I tell you, specific always means our variable is divided by mass. Yeah? If you have, for example, joule, the unit joule, you divide it by mass, you call the quantity specific. Yeah? You can, or if you have a volume, you divide it by the mass, it's a specific volume. And that's something we will use more often. And there's another important word here, an English word, it's the word flow. Do you know what the word flow means mathematically? Does anyone has an idea? What does it mean if I add the word flow? Don't be shy. Okay, explain you. Flow means the unit is divided by time. Yeah. If you have, for example, mass flow, and then you divide kilograms by time. It's a derivation of the mass. Or you can, for example, have volume flow. You mark it with a small dot here. And if you add the word flow, it means that you divide your volume by time. Okay, no problem. We will come to this point later. So let's have a look at the degree of efficiency. That's always something I will ask you. The efficiency is always something that will be asked in the exams. And maybe it's a good idea from time to time during this lecture, I will tell you when something is really important and when something is mandatory for the exams. And the definition of the efficiency is, of course, really important for the exam. There will be always questions about efficiency if we do exercises. Huh? So the efficiency is, we use the symbol eta. It's a Greek symbol. It's not an N, it's an eta. And it describes the power of confusion of a looseless machines by the power of consumption at the shaft of a work machine. Okay, then let's have a short look at the losses. We have to look at losses because in reality, all the fluid energy machines have losses, of course, and we can have a lot of losses by friction, by the clutch of the fluid energy machines, by the gears. We can have a lot of mechanical losses, and that's we have it in all machines, mechanical losses. Of course, we can have fluid losses. For example, if the design of our propeller is not really good, we have a lot of turbulence and fluid losses. So design of propellers or fans is really important. And we can have leakage losses. And the leakage losses happens, for example, at the gap between the propeller and the duct. I show you the computer fan. Here you can see the fan. We have the duct, and here's a small gap between the fan and the duct, and this will cause leakage losses. So if you have a good design of your propeller, you keep this gap really small, then you can have less losses. Okay, and of course, all these losses cost energy, they cost money, so we have to prevent losses. That's the same picture, just it's painted a bit different. Yeah, we can have here our losses, we have our gross capacity, we have inner flow capacity, we have inner leakage, we have outer leakage, and of course this outer leakage is much bigger if we don't have a duct around it. So if we have a propeller of an airplane, they have a lot of outer leakage. Yeah, it's they have always you can't rise your efficiency, for example, of wind turbine above 57% because you have so much outer leakage. Okay, so this means this is just introduction. We will come to wind turbines in more details later. And if you have a look at wind turbines, all the wind turbines, they don't have a duct. Yeah, if we had wind turbines in future with a duct, it would be much more efficient to use them. Yeah, but nowadays, yeah, you can imagine this duct will be really big, so we don't have this duct now. It's not practical. Okay, let's have a look at the total efficiency. So we have different small efficiencies. Yeah, for example, friction, fluid flow. We have small efficiency. We have, for example, loss of efficiency because of gaps. Yeah, we can have loss of efficiency because our bearings, gears, ball bearings, sealings. Yeah, this will all cause mechanical losses. And now, if we want to calculate our overall total efficiency, we have to multiply all the single efficiency. So this is also here you have to make your cross at this slide. Yeah, and keep it in mind. This law is really important. You have to, yeah, that's maybe something I have to explain. When it comes to the exam and you write the exam, you can write, you can get some help for your exam. You can write a sheet of paper where you write by hand all the laws and all the symbols and all the pictures you need. You can write it on your own, and you can use this helping sheet of paper for during the exam. Yeah. So if you write the exam, you should not take all the slides to this exam or all the old exercises. That would be too easy. But you can take one sheet of paper where you make your notes and make the most important formulas you need, and you can use it during the exam. Is this so it's good if I guide you through the slides now, and from time to time I say, oh, this is really important, then you can just add this formula to your sheet of paper, and you can use it during the exercises, and you can use it during the exam later. Did you understand this?
Yes.
Okay.
Are you allowed to write on both sides of the sheet?
Yeah, this question always comes from the students. Yeah, I will not control all the sheet of papers. Yeah, you can use both sides. You can use one side. You can use the side on the back too. You can write small. You can write big. Everyone has a different handwriting. You can write it with a computer. I don't care. Yeah, you can decide it on your own. And also a good hint from my side is exchange it with your colleagues. Yeah, discuss it with your friends or with other pupils, and send them or make a WhatsApp group and talk about it, what you want to have on this sheet of paper, because that always helps you to learn the content. Yeah, so you can use both sides, but you should not take all the slides. That will be too chaotic, and you should concentrate on one sheet of paper. But I don't care about what you write on it or how big or how small your handwriting is. Okay, is this Mr. Schröder? Does this answer the question? Hello, Mr. Schröder? Does this help? Okay. Okay, so guys, to the other ones, to the audience, yeah, I will mention this sheet of paper from time to time. We're at the beginning now, but I think you will know how I mean it. Okay. So let's have a look at the volumetric degree of efficiency. We can, if we have a propeller or if we have a fan, we can calculate the mass flow by the efficiency, the density of the sucked air, the number of rotations, and the pump or compressor displacement. It's also an important formula. We will need it later during the exercises. Okay, that's something about the energy. Yeah, I will not go into too deep detail about this efficiency, because this efficiency is only needed if we have a big temperature difference before and behind the fan. And this is more or less, this is never the case. Yeah, normally the temperature does not change a lot in front of the fan or behind the fan. So this is not so important. This again is a really important formula if you want to calculate enthalpy and enthalpy differences behind and before the fan. You need the heat capacity and the temperature. But like at the slide before, in most of the cases, there will not be a big temperature difference if you have propellers or fans or blowers. This is more important, for example, for gas or steam turbines, where we have big temperature differences. Here in this propellers, we don't have big temperature difference. Okay, that's the same. I will go on with this later because it's not so important. Genau. Here I've written down some points. You can go through it. You can read it on your own. I think I explained most of the parts. And let's come back to our blade, to our propeller. If we have our propeller, we have a twist of the propeller. If you look closely at the propeller of an airplane, or if you look closely at a fan, or maybe you have a fan in your room. Normally during the lectures, when I do the lectures at the university, I bring a fan with me, I bring a propeller and I show you, but I think you know how a propeller looks like. And if you look closely at a propeller, you see this angle will change. Yeah, it will at the axis in the middle of the propeller, the angle is higher. But if it comes to the ends, if you come to the end of the propeller, the angle will be much smaller. Yeah, and this is important because if you think about the propeller, it rotates, and in the middle you have a really smaller velocity of the propeller than if you compare it with the tips of the propeller. Yeah? So we have to change the angle that you can have at both, even in the middle of the propeller and at the tips of the propeller, you can have the same wind velocity. Yeah. Okay, and this triangle, you have to know something about vector mathematics, and we will, in the exercises, we will make some small exercises about these triangles, and we will calculate it together. but I think you all know a bit about mathematics. You have some basic knowledge in vector mathematics, and it will not be so difficult to calculate these velocity vectors. We will make a short exercise next time. Okay. Okay, yeah, here again, it's this triangle, this velocity triangle. And that's a calculation of this velocity triangles is always needed for rotating fluid energy machines. Yeah, you will always have this kind of plates, and then you had to calculate the velocity. Okay, so I think up to now, more or less, we come to the end. Here is again a kind of industrial fan, and I copied you this picture to the slides because I want to explain you also a bit about efficiency and the history. Yeah, this is a ducted fan, and it's a really old fan. It was used in former times, and we had the engine outside. Here's the electric engine, and we had a belt, and the belt drives the propeller, and then we can get the airflow. This is a modern fan. Yeah, this is a modern design, and it looks, if you look closely, it looks a bit different. For example, here the duct has an angle. Yeah, it gets more tiny at the end, and you can see the engine is inside the duct. Yeah, it's not outside, it's inside. Do you have an idea why it is better, why this is more efficient to have the engine inside?
Could it be that the airflow is cooling the engine at the same time?
Yes. And if you look closely here in this small gap, you see some fins. You can imagine you have to cool down your electric engine, and so you have two functions. Yeah, here at this old design, the engine gets hot. You have no cooling, but you have an airflow here. So that's not really efficient. It's better to place it here inside the fluid flow and to cool it by the air. And there's another thing that is not really efficient. If you imagine here this belt, there's a belt that drives the propeller. You will have a lot of friction. It's much more efficient to place it directly here behind the propeller. And here's something else that should be mentioned. You see here are the plates. Here we don't have a really good design. I think the engineers, they just made it by hand. But this design looks much more efficient. And you have here, you have a rotor inside, but you have here also a stator. We have some wings that don't rotate. And this will also guide the air more efficient. So this design can only be done by computers. You have to make a complicated simulation. And I also make a lot of teachings about computational fluid dynamics. I don't want to do it here in this seminar. We don't have enough time. But I also give seminars, for example, fluid dynamics, where I teach you how to make simulations about the fans. Okay. Another important quantity if you make design of the fan is, of course, a mass flow. You have to know how big your fan should be. If it's a big fan, I know fans for power plants are 5 meters in diameter, or you can have really small fans for computers. And you have to design your fan depending on how much air you need, how high the mass flow should be. And of course, if we speak about mass flow, we should also speak about volume flow. And I mentioned the word flow means always we have to divide it by time. So we have a volume divided or derived by time. And of course, the volume flow is always really important. If you make, for example, now we have also a project for a company called Ursa Farm. They make medicine and they have to design their ventilation systems in the clean rooms. And of course, the first thing they want to know, how much volume of air do I need for a climate in our rooms. Okay, here again is a small picture about a modern axial ventilator. Here you can see here the rotating plates. You can see here is a electric engine inside. Yeah, you can see your static wings. The static blades, they don't rotate. Only this part rotates. Of course, you have a nose here. Yeah, design of the nose is also important for efficiency, and you have here a duct. And the design of the duct is also really important for fluid flow and for efficiency. Yeah, we don't want to produce too much turbulence in this ventilator, because turbulence is always loose and friction. You can see it a bit in more detail about the design. Okay, yeah, or here we come to this point a bit later. I think it's more easy if we explain it during our exercises. And here again, we have also some impeller, a motor, and we can get here a lot of turbulence and losses. But if we have our static rotors, we will have less. We have more laminar flow and less losses. And also gears, I explained you about mechanical losses. If we have a lot of gears and if we have a lot of belts, they will cause also always friction and losses. So it's better to use the engine directly. Now that's more efficient. And of course, we want to cool down the engine. That's always important point. Heat is loose. If we have an electric engine and if we have a lot of heat inside this, the armature of the engine, that are always losses. Yeah? So it depends a bit on the metals and the materials to use efficient materials to prevent losses. Okay. The next important law is the ideal gas law. I think you should know it. We will use it in many cases later. You should make a cross at the slide. We will use it for calculations, and we can also have the real gas law, where we added this real gas factor to the ideal gas law. This is for our problems here. We will not use it so often, this law. Okay, this is again an important formula. It's a specific energy. I mentioned it before. This is something we always have to calculate, the specific energy for our fans or for our blowers or propellers. We have here, that's a very simple fluid energy machines. We have an axial fan and the flow will come, the flow of air will come inside here. It will pass out here. We will have different pressures in front of the fan and below the fan. We have different velocities, of course, and then we can calculate the energy, the specific energy based on pressure difference and velocity difference. This is, please make your cross here. We will often use this formula to calculate pneumatic work. Okay, this is, I don't want to go into too deep detail into this. This is more for steam and gas turbines. I don't want to go too much into detail here. We don't have big enthalpy differences for fans because we don't have really high temperature differences behind and before the fans. Okay, and here is also some slide about efficiency. If you mentioned a fan can have different number of plates. Here we see a fan with 3 plates. We can have two plates, or we can have more plates. Yeah, we can have 5, 6, 7 plates. Yeah, and normally the efficiency gets higher if we have higher plate numbers. Yeah. Okay. So the efficiency depends on plate numbers. That's also one of the last slides. It's a bit small. We will need it later for the exercises. If we want to design a fan and we want to buy a fan, if you go, for example, to a company here, KKK is a big company for fans here in the Rhine region. And if you ask KKK, how we want to buy a fan, we need a volume flow. Maybe if you want to build a hospital, or if you want to design a ventilation system for a house, we need a special volume flow of air. And then we can go to the company, we can order a fan, we can ask for the volume flow, and they will look here inside this diagram. They will maybe have, I say we need 20 cubic meters per second, and then they can look which fan suits this demands, and then they can choose a fan with a specific work. Yeah, the Stutzenarbeit is unfortunately a German word. I will change it afterwards. This means specific energy. Yeah, Stutzenarbeit is a German word for energy. Yeah. Okay. Okay. Go over this. Okay, that's one of the last slides. From time to time, when I show you the slides and when I give you some famous laws or some famous numbers, or when I explain you something, from time to time I go a bit through history and I explain you a bit about the people that invented the laws, and one very famous person is August Camille Edmond Retau. And maybe you know Saarbrücken, we're really close to France, and a lot of famous scientists in fluid flow and a lot of famous scientists in mining have been French people, yeah? Because in the time where they invented this laws, yeah, in the maybe 200 years ago, a lot the science in French was really good developed. So they invented a lot, and this was a famous mining and mechanical engineer, and he also founded a big company, and today it's known as Alstom, and they build trains and subways and a lot of mining facilities up to now. And he formulated here this flow rate invariant. Okay. It's also a map about, it's the same map than this map. It's really similar to this map. And from time to time, we have to use these maps and we have to go through it. This is just from another company, the company of Voigt. Voigt are also a company. They are, for example, here in Kaiserslautern. They're located in different locations. Voigt is a really big company for blowers and for fans. And now if you want to buy a fan from the company, you have to tell them, oh, I need a big fan for maybe 100 cubic meter per second. And then they will go through this diagram. You have to tell them about pressure drop, you want to have pressure drop always costs money. It has something to do with costs, and then they can choose a fan. And this characteristic, I want to come to the end now. It's nearly 9:30. This map, this efficiency map or this diagram, we will need it later for the simulation exercise. I want to show you a bit about simulation, but not too much. And we will need it. I want to go really fast now through the first steps, but we should proceed with these steps next week. And then next week, please, before, here is in the slide is a small example. Please, I want you that you look through the slides carefully and try it out on your own with the tool. And then you should do this small exercise here for our ducted fans. And I will also give you a movie how to do it. I made a movie about how to do it on YouTube. I will send you the link, and I want to go to Moodle again to show you where the exercise is. Please have a look here. Here is the slides. Okay. Hello, are you still here?
Yeah, and we can see.
Yes.
Okay.
Yes, we're
Give
here.
me some life science. I talk a lot and I haven't heard a lot from you. Okay, all the slides I showed you, they are here in Moodle. You can go through it again. And Mr. Schröder, I think you can stop now the movie.
All right.
Okay, because this is not, you don't need this information in the movie. These are all the slides.